Hi everyone, these are two ideal gas law example problems. Here we go. Determine the pressure inside a 5.0 liter container if it contains 3.0 moles of gas at 40 degrees Celsius. Let's get our labels in there to help us interpret and wrap our head around what this question is getting at. Determine the pressure. We're looking for P inside a 5.0 liter container. 5.0 liters is the volume. When I'm working with the ideal gas law, the volume must be in liters, and I have it. So I run that through my mind really quickly. If it contains 3.0 moles, that's N. No brainer there, moles are the moles. Of gas at 40 degrees Celsius, this is the temperature. And it's already in the back of my mind that I'm going to have to convert that into Kelvin as I move forward. You might be the kind of person who likes to have a formula to help you feel organized. It's PV equals nRT, which we need to manipulate to solve for the pressure. We divide both sides by the volume. Those V's cancel, and that leaves us P equals nRT over V. Now we can start to substitute our values into the equation. N, 3.0 moles. R is the ideal gas constant. It has a discrete value, 8.314 kilopascal liters per mole Kelvin. Now we have our 40 degrees Celsius, which we must convert into Kelvin. That's 40 plus 273.15. And all of that is going to be divided by the volume, our 5.0 liters. From there, we can calculate 3 times 8.314 times 40 plus 273.15 divided by 5, which is 1,562.11746. This is our raw answer. We need to think about the significant digits and the units. The numbers in the question all have two significant digits, 5.0, 3.0, and 40. So I need to round off my answer here so that it also has two significant digits. Here, I'm going to have to use scientific notation because we're up in the thousands, but we only need two significant digits. It's 1.6 times 10 to the power of 3. And we need the units. If we look at the algebra, the moles cancel, the liters cancel, the Kelvin cancel. This is going to give us the pressure in kilopascals. A second example. At what temperature will 10.5 grams of ammonia exert a pressure of 85.0 kilopascals on a 30.0 liter container? Again, I'm going to throw some labels into the question to help me with my interpretation. At what temperature? We're looking for T. We have 10.5 grams. Grams, that's the mass. As soon as I see mass, I start to think, oh boy, this is maybe going to be a two-step question. I might have to use molar mass. Here, the chemical ammonia is going to make a difference. A pressure of 85.0 kilopascals, that's the P. And we have a 30.0 liter container, the volume. I've started to think about what we can do. when I think about the formula, PV equals nRT, if I just run through a checklist, we have a pressure, we have a volume, we're looking for the temperature, we know the constant, but we don't have the moles. We have a mass instead. So we have a two-step problem. It's a good rule of thumb that throughout the course of the whole unit, as soon as we have something about mass in a question, that really does mean it's going to be two steps. Here, we have the chance to do mass over molar mass. Then we can take our answer and use it in the ideal gas law formula. So let's move forward. We have the mass, 10.5 grams. Over the molar mass of ammonia. The molar mass of ammonia. That means we need the formula, we're going to be using the data booklet and adding up all of the individual atomic masses. Ammonia has the formula NH3, 1 nitrogen and 3 hydrogens. When I use the data booklet to figure out the molar mass, it's 17.04 grams per mole, mass over molar mass. And I can do this operation, 10.5 divided by 17.04. 0.616197183 moles. This is not the end of the question, so I'm not going to round this number. I'm not going to do anything to it. I'm just keeping it right on my calculator. I'm going to carry it forward here up there. Now let's manipulate the ideal gas law formula. The temperature is PV over nR. PV over nR. The pressure was 85.0 kilopascals. V, the volume, 30 liters. 30.0 liters. This is over the moles. That's the answer that's just sitting on my screen. So I'm going to write it like this. The answer that's just sitting on my screen, 0.61619. Multiplied by R, the ideal gas constant, 8.314 kilopascal liters per mole Kelvin. We have to be really careful now with our calculator work. If we got this far, it'd be a shame if we didn't get the answer. So here we go. 85 times, pardon me, not 35, 85 times 30 divided by our answer times 8.314. We get 497.7490635. Our raw answer. We need to go back to look at the question to think about our significant digits. The values in this problem all have 3 significant digits, so I need to round off my answer appropriately. 497.7 is going to round up to 498. And this was the temperature, Kelvin. This question just asks, what's the temperature? So I can leave my answer in Kelvin. I have to be careful for those times where the question might specifically demand an answer in Celsius, where we would have to do this conversion back. However, this question doesn't do that. When we're working with the ideal gas law, we have snapshots. We're not having a before and an after. There's lots of different values in play. Pressures, volumes, temperatures, maybe even sometimes a mass. We need to take our time with our interpretation. We don't have to have labels, but it can absolutely help you choose the formula. Don't forget to convert into Kelvin. As part of the calculation itself, you might prefer to do that conversion on the side. Watch out for those significant digits. There are going to be moments throughout the course, like here, where we had to use scientific notation to satisfy our sig-dig rules. We have sometimes one-step problems where we're solving for the pressure, the volume, the temperature. However, as soon as mass becomes part of the question, whether we're solving for the mass or given the mass, right away then that's a huge sign that we're going to have to do two steps. Here, we first used mass over molar mass, and then we carried our answer forward into the ideal gas law formula. It was a little bit strange to have it show up in the denominator. You have to be careful with how we use our calculators so that we do end up with the correct answer. The final thing, watch out for those times where we're solving for temperature. If it's left a little bit ambiguous like this question, we can leave our answer in Kelvin, but sometimes we might have to convert it back into Celsius. And I hope that helps.